Hello everybody, let us start our discussion today and we will continue on kinematics of rigid bodies. What we have learned so far is the following, that we can represent the orientation of a body with three angles, and these three angles can be rotations about successive rotations about three axes. What we are going to describe, or what we have been describing, is the rotation of a rigid body, and say this is my rigid body. It's oriented somewhere in space, and first we consider a vector which goes to the center of mass of this rigid body, and that vector is obviously having three components. If I choose, so far we have been doing this, so we have chosen a reference system x, y and z, which we called the reference system which is fixed in space, and then we chose a reference system which is fixed in the body, which we call the body set of reference systems, and these we labeled as the primed axis. Now, to describe the motion of the rigid body, what I need to tell you is that how r changes with time, and that's just a translation. And there are three translations essentially. And let me just remind you how the translation happens. So what happens is r with certain times goes to r prime, which will be given as r plus, if it is, let us say that it's an infinitesimally small translation, so some epsilon times some other vector. Let's say it's a translation vector. The other changes in the can be the orientation of the rigid body, and that can be written as how orientation changes this also has 3 degrees of freedom, right? And we ask the question how this can be represented mathematically, just like we have represented it here, represented the translation there. The representation can be the following way. We describe the original set of axes like this, and this you can say is the body set of axes. At the start of the motion, we have said the body and the space set of axes. So this is space set of axes, this is body set of axes, and you can imagine that I have chosen them aligned to start with. Usually you will first choose the body set of axes because that may have certain advantages with respect to the symmetry of the body, so that we'll learn later, and accordingly you choose the space set of axes. So choose the space set of axes aligned to the body set of axes, and then you say that over the time how it changes is given by successive rotations, and that rotation we represented in terms of some SO3 matrix. So 3, because it's 3 cross 3 matrix, it's an orthogonal matrix which we saw that has certain properties, and it's special orthogonal because its determinant is 1. And then if you do that in general, then I get essentially the directions of the new coordinates. So that is what we learned, how to represent the three rotations by SO3. And remember that that can be written in successive rotations. So we talked about Euler angles and all. So this need to have three independent components because it has 3 degrees of freedom only. The rotational degrees of freedom is 3, and it can be given in terms of 3 rotations, in terms of 3 Euler angles. And in case of the Euler case, we said that so first we do a x rotation, then we do a z rotation, then we do a x rotation again. And this we wrote in the following way: the total rotation matrix, if I call it T, the x rotation, so let me write a superfix x over there and say the x rotation is about theta. Then I have z rotation, which is about say phi, and then I have an x rotation again, which is about psi. And we had written down the individual of these, which are very simple because one of the axis has to remain fixed and it's just a 2 rotation about that axis. And I asked you to calculate this in the last, at the end of the last class. It looks like this matrix. It is called A in Goldstein. I have just copied this matrix from Goldstein, but essentially this is the matrix that we are talking about. So this is what we have done. Today we will see how to represent the same 3 rotation in a different representation today. And at the end of the class today, you will see several reasons why one want to represent the 3 rotation in a different representation, which we will discuss today. Okay, so let us start that. So what this representation will be, remember what we need to represent 3 rotations which will be given by 3 independent numbers. And the rotational degrees of freedom, or the change in the rotational degrees of freedom of a rigid body, will be given by how these 3 numbers changes independently as a function of time. Okay, so what we want to do, what the way we do is that we start with a complex matrix today, and as the time unfolds we will see how we can get up to only 3 independent parameters. And we start with a 2 by 2 complex matrix instead of a 3 by 3 matrix. Okay, so we start with such a matrix. Let me call this Q, and it's in general can be represented alpha, beta, gamma, delta. Okay. First, what we demand is that this matrix is unitary. Which essentially means that its conjugate transpose is same as its inverse. Or I can write it in 2 different ways, but let me write it this way. QQ dagger will also be 1. Now, this is the first condition that I put in for the matrix. Let's see what this condition gives us. So if this is Q, what will be Q dagger? Q dagger will be its conjugate transpose. So this will remain as it is with the star, and the off diagonal will change their location with the star. right? So this condition or either of these conditions will lead us to alpha, beta, gamma, delta here. This equals, so this is the unity matrix. So what does this give us? Well, let us see. To start with, here, because I have 4 complex number, each complex number has 2 real numbers, which means alpha, beta, gamma, delta are actually 8 numbers, right? So this is 8 numbers. But I need 3 rotations, so somehow I need to get 5 conditions on Q such that I'm left with 3 out of these 8 numbers. Now let us see what the unitary condition gives us. So let's look at the diagonal elements first. So the first diagonal element is alpha alpha star plus beta beta star equals 1. Now alpha alpha star is manifestly real, beta beta star is also manifestly real, so this gives me one condition. Similarly, the other diagonal element will give me gamma gamma star plus delta delta star equals 1, and that also, because of the exact same reason, gives me one more condition. If I look at the off diagonal elements, I will get alpha gamma star plus beta delta star equals 0. The off diagonal elements are 0 because the right hand side is a unity matrix. Now this alpha gamma star is not real, so this is actually a complex equation that gives me two conditions. If I look at the other diagonal element, it will turn out to be just the conjugate of this, so that doesn't give me anything extra. So these together is are 4 conditions, but I needed 5, right? So what is the other one? Well, if I look at the determinant of this equation, I get determinant of q dagger equals determinant of the identity matrix, which is essentially 1. And determinant of q dagger can be written as determinant of q times determinant of q dagger. So that equals 1. Now this essentially sets the determinant of q and the determinant of q dagger multiplied equals 1, but it doesn't tell about the individual determinants. But if I choose now that determinant of q equals 1, then I get one more condition. Now you may think that, okay, so let us write what is the determinant of q. So determinant of q equals 1, this essentially means alpha delta minus beta gamma equals 1, which again apparently is a complex equation because alpha times delta is a complex number, beta times gamma is also a complex number, and in the right hand side I have essentially 1 plus I times 0, so it's a complex equation, but it actually doesn't fix two numbers because one is already fixed. And how you have fixed one? Well, the magnitude of the determinant is actually fixed by this. So because the magnitude of the determinant is already fixed by this, This only fixes the phase. Okay, so that is the extra. It actually fixes both of the phase and amplitude, but the amplitude is already fixed by these four conditions. So this gives you one more independent condition, and that becomes the total 5 conditions. So which means now, using these 5 conditions, using these 4 complex equations which has 5 conditions, I can identify three parameters, or I can write Q in terms of 3 parameters. So let us see what these conditions give us. So let me box the important equations here. So I have written so many. This and this. Okay, so now let us see what we get out of these. So let's start with this equation. I can write delta from that equation in terms of everything else. And to do that, I first have taken a conjugate. Imagine I have taken a conjugate. So I get alpha star gamma by beta star. Okay. So once I get that as delta, I put that in the last equation, alpha delta minus beta gamma equals 1. So I'm doing some algebra, but I will see that at the end something nice should come out of it. Okay, so if I do alpha delta, so that is alpha times delta is this, so alpha star gamma by beta star minus beta gamma equals 1. And if I take say minus gamma common outside, minus gamma by beta star, so I get alpha star plus beta star equals 1. But you see alpha star is already 1, so which means this gives me gamma as minus beta star, right? Now if I put that information into this, so then this combined with this, what does it give us? It tells us that delta is equals minus alpha star, gamma is minus beta star, so I can write minus beta star here divided by beta star. The minus goes with minus, so delta becomes alpha star. So again I get these two relations. Right? And you see, by doing this, I have not used one equation, which is, I have not used either gamma star plus delta star equals 1 or alpha star plus beta star equals 1. So one equation is still left. But now you see, gamma I can replace by minus beta star and delta I can replace by alpha star in my original matrix. So now my Q, I can write my Q as alpha and beta and then gamma is just minus beta star, and delta is alpha star. And because I have written everything in terms of alpha and beta, so I write alpha alpha star plus beta beta star. This is also a condition which has to be satisfied. So alpha and betas are not completely independent. There is one condition between them. So now if you count, I have 2 in alpha plus 2 numbers in beta minus 1 condition above. So I have total 3 independent quantities which is specified in my Q. So this must be that complex 2 cross 2 matrix which may represent a rotation. Okay, so this is an important information that we have got so far. So let me write it again and keep it in a box. So this is what we will carry forward for some time now. Okay, so the next thing that we will like to see is how to represent this in terms of, or how to use this to represent rotation. Okay, now because it is a complex 2 cross 2 matrix, we need to be a little more ingenious. Remember that for rotation, I have 3 components, x, y, and z. I have to change x, y, and z, all 3, but I have a 2 cross 2 matrix. So a simple representation of the vector like a column vector or a 3 component object does not work here. So how to represent the orientation? Remember, Q is giving you the change in the orientation. How to represent the orientation itself? So let us start by trying with this. Obviously it will work, that's the only reason I am trying it. So you write a matrix and you can check that it's a Hermitian matrix. It's easy to check that it is Hermitian, so I'll not show it to you, but this is the matrix that I write. Sometimes I will use a shorthand for this, where this z and minus z will be as it is. For x minus iy, I will write x minus, and for x plus iy, I will write x plus. Okay, so that's just a shorthand notation for the same matrix. Now you can see it's a 2 cross 2 complex matrix. You can check, it's obvious that the trace of this matrix is 0, right? Z minus z is 0. What is the determinant of P? Determinant of P is z times minus z is z squared, and if you work out the multiplication of the diagonal elements, it will be so this is essentially minus of r squared. You see, it must so happen that the determinant of the matrix P has to be preserved. So this must be preserved. In a rotation, right? So the transformation of P that will happen, the transformation will happen by means of Q, and the transformation will be so such that the determinant of the matrix has to be preserved, and that we are saying that because the determinant of matrix is just minus r square, and we know that the length of a vector is preserved in any rotation, right? So how do you represent the rotation? So the rotation or the change in orientation of a rigid body obviously is P going to P prime, which is that is a change. That in terms of P is now not as simple as it was before. It is now Q, P, Q dagger. But remember that Q dagger is nothing but its inverse because it's a Hermitian matrix. I'm sorry, it's a unitary matrix. So this I can also write as QPQ inverse. And if you have studied matrix multiplication, which I guess you have, this amounts for a similarity transformation. Remember, similarity transformations preserves the eigenvalues. Eigenvalues, if I can make P diagonal, then eigenvalues are the diagonal elements, and the determinant is the multiplication of those diagonal elements. Similarity transformation preserves determinant and trace, right? So the trace of P will always be 0 and the determinant will be preserved as it is required by a rotation. Okay, so this is how now I will have a change in the orientation of a rigid body. P is the P will represent a particular orientation and Q will bring in the change. Okay, so let us see that what is the parallel between the SO3 representation and this representation, okay, which I will call SU2, and we'll see why it is called SU2. So let's draw some parallel between SO3 and this particular representation which we are talking today about is SU2. Okay, so let me draw a line between them. Now remember that this S stands for spatial, where we chose that determinant equals 1. This else also stands for spatial, where again we chose determinant equals 1. O stands for orthogonal, so these matrices were orthogonal. So its transpose is same as the inverse. Here these are unitary, so its conjugate transpose is same as its inverse. And these, the components of this matrix, this is first a 3 cross 3 matrix and the components are real. Here it's a 2 cross 2 matrix and the components are complex. Okay, so there is some This is essentially what are the two transformations. There are some similarities and some not so similarities. Now, in this case, if I say I am going from x to x prime, and then I am going from x prime to x double prime, so I am doing two successive transformations, and say this transformation matrix is T1, this transformation matrix is T2. So we can ask the question, what is the transformation matrix from x to x double prime, and say that is T3. Then we saw that T3 is given by T1 happens first and then T2 happens second. Here, let's see what happens in the case of SU2. So again, I am dealing with the transformation x to x double prime, x to x prime and x prime to x double prime. The transformation from x to x prime is, say, q1, and x prime to x double prime is, say, q2, and directly from x to x double prime is, say, q3. Okay. So let's ask the question, what is, how do I write the final state in terms of the initial state? Now the final state here I represent by P, so I call it P double prime, which is after the two transformations. So X double prime here represented as P double prime. That will be the way we are transforming Q2. The previous one was P prime and then Q2 dagger. But then P prime has come from a transformation which is Q1 from P, Q1 dagger, and then Q2 dagger. So this 2, if I call Q3, then I have to call this as Q3 dagger. Then only this relation will look like a transformation from P to P double prime or X to X double prime. So which essentially means that Q3 dagger is nothing but Q1 dagger, Q2 dagger. Which we know is same as Q2, Q1 whole dagger. So the rules of the matrix multiplications does work here. So what we can do now is that we can choose. So this is our conclusion so far. We can choose any 2 cross 2 SU2 matrix as giving rise to the transformations we want, or giving rise to rotations. So remember now, Q we are representing in terms of, you can write it in terms of 4 parameters: alpha, beta, gamma, delta. Or in terms of 2 parameters, alpha, alpha star, beta, beta star. With alpha, alpha star plus beta, beta star equals 1. Now these parameters have a name, just like we had names for the angles. We call them Euler line angles. These are called Cayley-Klein parameters. Also remember that a state, which is what changes if there is a rotation, we represented this as z x minus x plus and minus z. So if I have a rotation, so let me write down. So this is change in orientation, change in state. State is the orientation in this case. That is represented by this. And the state itself, the state of which angles it is represented by P. And we also said that P prime, if there is a rotation, P goes to P prime, and P prime, which is obviously Z prime, X minus prime. I guess you remember what are X minus and X plus is. X minus is X minus IY, and X plus is X plus IY. And this will be Q, which is alpha, beta, gamma, delta, P, which is Z, X minus, X plus, minus Z, and then Q dagger, which is alpha star, delta star, beta star, and gamma star. Now you can write some of these in terms of alpha. So I can change all the stars in terms of the non-star values of alpha, beta, gamma, delta. So I'm not doing the exercise. I will just point you to where what I can use to do that. I can use these two essentially. So whenever I see a star, I will replace that with, so if I see beta star, I will replace that with gamma, or if I see beta, I will minus beta star, I will replace that with gamma, etc. If I have delta star, I will replace that with alpha. By doing that, I can write the right hand side of this in terms of, can be written xyz and alpha, beta, gamma, delta. Right? Now the left hand side, this is the right hand side. This can be written in terms of x prime, y prime, z prime. Right? Now I can actually do one thing, which is, see, remember that P represents the state of the vector at a given moment of time or a given state of rotation. So I can write this as x prime, y prime, z prime. So this will be fairly complicated or lengthy calculation, not complicated, rather lengthy. So I will not do it here, but I can bring back this form. And remember that this will be the SO3 matrix. This will be SO3 matrix. I can bring back that form. So if I do that, the matrix that I will get as that SO3 matrix in terms of the Clay-Klein parameters will be the following. This matrix. So you see, again, I have taken it from Goldstein, but you should calculate once in your lifetime and verify that these are the parameters that you get out of it. Now, this alpha betas, see, the entire Q matrix can be written in terms of alpha and beta only. So there is one way of we can represent this, is that I can write alpha equals some E0 plus IE3 and beta equals some E2 plus E1 plus IE2. And you can see this condition requires alpha alpha star is E0 square plus E3 square, and beta beta star is E1 square plus E2 square. So I have this equals 1. So this is another interesting ways of representing the same thing in terms of these parameters E0, E1, E2 and E3, and there are 4 parameters, so I needed one condition, so that is that condition. E0 square plus E1 square plus E2 square plus E3 square is 1. Okay, and you may be very angry on me at this stage, asking why would I bring in another way of representing the same thing. Now that will be again clear shortly. You will see that in terms of these ease, first of all, there is an ease of writing the transformation matrix in terms of the ease, and then we'll get, while I try to write it in terms of ease, we'll see that we get certain form of the matrix which brings us more insight. Now just like I got this SO3 matrix written in terms of the alpha beta gamma deltas, I can write this in terms of, so these are written in terms of alpha beta gamma deltas. I can write this in terms of E0, E1, E2, E3 also. That is also possible right now because I have defined them. And then this is how it looks in terms of E0, E1, E2 and E3. Let us ask the question now that in terms of this ease, how can I write the rotation about an axis? Okay. In terms of Q, sorry, how can I write the rotation about an axis? So let's start with rotation about Z axis. Now I will not derive it because that will take quite a bit of time. You can look at Goldstein for the derivation. But what happens for rotation about Z axis? X goes to X prime, which is, so this is by an angle phi counterclockwise. So this is X cos phi plus Y sin phi. Y goes to Y prime, which is minus X sin phi plus Y cos phi. So what we like to write down, like to do is to write this down in terms of X plus and X minus. So if you write x plus prime, now how does that transfer? Or x plus, how does that transfer and go to x prime, x plus prime? So x plus goes to x plus prime. Now this, let me write this directly, as simple as that. Well, you may say why? Well, let's work out what is e to the minus I phi x plus. It is cos phi minus I sin phi, and x plus is x plus iy. If I collect the real parts, you get x cos phi plus y sin phi. And if you collect the imaginary parts, you get minus x sin phi plus y cos phi. Remember, the left hand side is x prime plus iy prime. So if you compare the real and the imaginary part in the right hand and the left hand side, you get back this. So this is a very nice looking way of writing down the transformation from x plus to x plus prime. So you can check now that x minus will go to x minus prime in the following way. In fact, the entire transformation, which we wrote as about z by phi counterclockwise, so this was my SO3 matrix. This now will corresponds to a Q matrix, which is again phi. This you can verify. How will you verify this? Well, it is simple. This is the matrix that I have to use here. If I use the matrix, that matrix here, then you can see whether you get a z rotation about z axis. You know that how z prime, x prime, y prime will be related to x, y, z, and using that you can verify. You will see this happening. I'll not prove it for you, but what I will do is I will write down the other ones. So these are all SO3s. So let me do a little rearrangement of what I am doing here. So this side is all SO3s, this side is SU2. So this is x rotation by theta. This in terms of Q will be and the psi rotation, it is simple that because it's also about z, it will be z the same as q phi z, but now e to the I psi by 2 instead of e to the I phi by 2. And if I ask you what is your q, which is the 3 rotations in Euler sense. So first a rotation by phi about z axis, then a rotation by theta about x-axis, and then a rotation by psi about z-axis. And now, because two of them are diagonal, these two are diagonal, it is a lot easier to multiply and write the q. You remember how complicated it was, and I did not work it out. I asked you to do it. And okay, so I ask you to do it again here. So calculate what is this. But this is lot easier now. Okay, so that is one calculation. The other homeworks, let me give you other homeworks. Alpha, beta, gamma, delta in terms of Euler angles. Similarly, E0, E1, E2, E3 in terms of Euler angles. Okay. So this will give you an idea about the relation between different types of parameters. So you have a couple of things to discuss, and I promised to you why it is interesting to write Q in terms of E0, U1, E2, and E3, yet another set of parameters. So let us discuss that now. And one realizes that, so I have this P which is representing the state of rotation. And you see, it's a state of 3 rotations. In case of, if I have a simple XYZ to represent any orientation, remember that XYZ was the X prime, Y prime, Z prime was the 3 directions for the body set of axes. Then obviously any vector I write as unit vector times x cap x prime plus unit vector along y prime times y prime, and then unit vector along z prime and the components along z prime. Similarly, P should be, though it is represented completely differently, not in terms of x, y, and z, but it should have 3 components. And one can write this actually in terms of 3 components, and this is in the following way. So the x is the component, and the unit, if you wish, the unit vector is represented by a matrix which I call sigma 1, and then y is the component, say, and sigma 2, and z is the component, say, and then sigma 3. Okay, so if I consider these as these are the components of a vector sigma, and let me write it with a 2 vector sign, because you see that the components of these vectors, each component is a matrix. So that is the, so these are the components of that, right? Then P is nothing but R dot sigma. And it turns out that sigma can be, the components of sigma can be written in the following way. I can call it sigma x or sigma 1, doesn't matter, but they can be written in this way. If you have not identified them already, they have a name, and that will be clear later why they have a name like this. These are called Pauli spin matrices. Just consider this as a name for the time being. For a little while. Hold on to your all queries. Now, if I have these three, and if I add to this the identity matrix, which is 1, 0, 0, 1, I can represent any SU2 in terms of sigma, 3 sigma components and I. In fact, Q is 1 SU2. Now this I called I0. Okay, let us call it I. Identity plus I E1 sigma 1 plus E2 sigma 2 plus E3 sigma 3. Okay. Now again you can verify that. It can be written this way. Let me show you one thing. The rest you can verify. Okay, so let me tell you how to verify this. So first you have to write Q in terms of E0, E1, E2, E3, which I have asked you to do somewhere earlier, or I have shown you actually how to write in terms of E1, E2, E3. And then once you have written it that way, then you have to compare and then check, get out the sigmas. So let me show you one example, not for with Q but with P. So remember that P we wrote like X sigma 1 plus Y sigma 2 plus Z sigma 3, which is X sigma 1 is 0, 1, 1, 0 plus Y sigma 2 is 0 minus I 0, and Z sigma 3 is 0, 1, 1, 0, 0 minus 1. So if I just do matrix addition, you will get in the first, you will get Z because both of these are 0. This is 0 and this is 0. In here I will get X minus IY. Here I will get X plus IY. And the other diagonal component will be minus Z, which is essentially what our P was, right? So this makes sense. On the other hand, if I look at say Q theta or say Q phi, let's say Q phi. Q phi is e to the I phi by 2, 0, 0, e to the minus I phi by 2. So try to write this in terms of sigma and E. So Q theta, for example, this is easy, so I'll do that. If I take cos theta by 2 outside, then I can write it this way, plus This is plus, this is not minus. Okay, now let me not go into more detail, but anyway, so let me tell you. So you can see that now if I compare q theta with the definition of q written here, it's clear that cos theta by 2 is E0 and sin theta by 2 is E1 in this particular case. So you can actually write all the three q's I have written here, where here, all these three q's in terms of the sigmas. Okay, so that's all your homework. I'll not go into any further detail. Let me tell you one interesting thing. So we have learned one. So let's summarize first what we have done. So today, last time we learned about this representation which gives rise to rotation. So it's generator of rotation essentially, which we called the SO3 representation, spatial orthogonal, three-dimensional, and we saw one case in terms of Euler angles. Today we have learned in terms of a different representation which we called the SU2, spatial unitary 2 cross 2 complex numbers. And we saw that how to represent in terms of SU2. The state vector now is also represented by a matrix, and the transformation is not as straightforward as it was before. Now the transformation is given by this. Transformation as generated by the rotation matrix, or this SU2 matrix is generated is given by this, which happens to be a similarity transformation. And we'll see that why it is important to get a similarity transformation there. And at the end, we saw that both the state vectors and the transformations can be represented in terms of polyspin matrices. Okay, so that's what you have learned so far. So the rest of the discussion is why this SU2 representation of the rotation is important. So that is what we will see a little bit today. So let me remind you at the beginning that remember that q phi is e to the I phi by 2, 0, 0, e to the minus I phi by 2. It is this phi by 2, that half factor, which carries something extra in this representation. So let us talk about that. Well, the corresponding matrix T phi was Z rotation, so it's cos phi, sin phi, minus sin phi, cos phi. Right? What if phi is 2 pi? Well, 2 pi corresponds to one complete rotation in the real space, right? So the z-axis, or the rotation about the z-axis, say my x was this way and y was this way and z is this way. When I do a complete rotation, this will come back to the exact same orientation, a complete 2 pi rotation, right? And if you look at this, T phi, so T phi equals 2 pi, indeed is an identity matrix. Cos phi is 1, sin phi is 0. Which is what I expect. The complete 2 pi rotation should bring us back to the original form. What about q phi? Well, these are all z rotations, so I may put a z over there. And q phi is having a pi by 2. So I get e to the I pi this, if this is phi equals 2 pi, that is not identity but rather this with a minus sign, which essentially means for each SO3 matrix there are two SU2 matrices. So what do I mean? I mean that if phi equals to 0, I get the identity matrix here in SU2, and if phi equals to 2 pi, I get minus the identity matrix. So for each SO3 matrix, so say T, I have to identify both of this Q and minus Q as the same. Otherwise, in space, I will not come back to the same orientation. Right? Now, this is interesting because now you realize that the mapping from SO2, SO3 to SU2 is not a one-to-one mapping. One objects in SO3 corresponds to two objects in SU2. So the degrees of freedom, if you consider these to be same, then only the number of matrices in SO3 will correspond to the same number of matrices in SU2, or SU2 actually have twice the number of possible rotation compared to the SO3 for the given set of parameters. What if these two separate things actually represents two separate physical state of the system? What if when I do 2 pi rotation with SU2, it actually gives a different state of the system? Well, in terms of SO3, in terms of the SO3, it cannot give a different representation of the system. But in terms of SU2, there is a chance that it can have a different representation of the system. Now, in classical mechanics, this doesn't make any sense, because in classical mechanics, SO3 gives you the exact number of possible ways you can arrange the system. This extra degrees of freedom, if you wish, which can be distinguished between these two different states, comes handy in quantum mechanics, where you have an extra degree of freedom, which you call the spin degree of freedom. And then this type of objects where you distinguish minus q and plus q are called spinors. And they represents the spin degree of freedom of the objects. Now this is the connection between, so when you say spin angular momentum, this is the connection between the angular momentum in classical mechanics and the spin angular momentum in quantum mechanics. You see, remember that these q's or the t's are the things which are generating the rotation. And the generators of a rotation is the angular momentum essentially, which you will learn in quantum mechanics in more detail. It turns out that such a rotation type transformation can also be generated by the spin of the system, or by change of the spin of the system. So there you distinguish between minus q and plus q. So it turns out that if it is a classical mechanics problem, SO3 representation works very well, and you can go to SU2 representation also identifying each minus q as same as plus q. But when you go to quantum mechanics and you have to bring in the extra degrees of freedom, which you call the spin degree of freedom, particularly spin comes in because of the fact that most of the electrons are relativistic. Or if I have to represent a relativistic electron, then I need these objects called spinors as my state function or wave functions. And there is no escape from the SU2. You have to use SU2. You cannot use SO3 anymore. And you have to use the fact that minus Q and plus Q are different. Okay, so that's where I will end today's discussion. And this is about the two representations that we have learned. Thank you.